A quick question. A frame with a fixed shape is moved around, it's actually moving with constant velocity along this direction, but this time the magnetic field is not entirely uniform. So the magnetic field is basically pointing towards us with a strength of 2 Tesla in this region, but in this region it is pointing into the screen and it has a strength of 3 Tesla. Alright, so in this situation, of course, the area doesn't change, the shape of the frame doesn't change, it just moves. So there's, even for this reason, there's a time-dependent flux, and so as a result there's a current in there. So again, the questions are finding the EMF, the resistance is also given, so finding the amount of the force that must be applied to keep it moving with constant velocity, and then the discussion of the conservation of energy. So let's start with the basic one. So the rest is kind of straightforward. Basic one, finding the EMF, but to be able to do this, of course, we need to compute the flux first. So let's then draw this picture again. So this is our frame. We choose a direction in here to measure our EMF. Associated with that direction, there's also a direction of the area. So the area vector is like that. What do I need to do? I need to compute the flux, basically the flux at time t. So that's B dot dA integral. The magnetic field is not uniform now. So magnetic field is pointing out of the screen in some region and into the screen in some other part of the region. So there's some kind of a boundary in here that separates these two regions. What are the side lengths? So let me go back to the question again. So the side lengths of the frame are A and B. There's this plane in a way that separates these two regions with different magnetic fields. So the distance of the right side of the frame from that plane is v times t. So that means at time t equals 0, the edge of the frame was just at that region. So that was the position of the frame at time t equals 0. So in any case, so therefore that distance is vt. So that means this distance is b minus vt. And so therefore this distance is a. So as a result, when we are computing the flux, I have to compute the flux coming from these two areas separately. So let me write this contribution first. Since the magnetic field is in the same direction as the area, we get a positive value in here, B1, the strength, multiplied with the area of that region. So that's A times Vt. And then we consider this surface. In that case, the magnetic field is opposite to the area. So therefore, from the dot product of these two vectors, we get a minus sign. So let me write minus in here. B2 times the surface area. So that's B minus Vt. Right, that's basically what it is. So first magnetic field was 2 Tesla. I need to remember these values. A is equal to 2, B is equal to 3, and velocity is 0.3. Multiplied with 2, multiplied with 0.3 t. And then we have minus 3 times 2 times, this was 3 minus 0.3 t. So as a result, I get minus 18 as the constant term in here. And then I get plus 10 multiplied with 0.3. So plus 3t. Unit is Tesla meter squared, where time is in seconds. It's just expressed like that. So therefore, the EMF is equal to, by Faraday's law, that's equal to minus 3 volts. So it is minus 3 volts along that direction. Or if you want, it is plus 3 volts along the opposite direction. So the positive current is going to flow in the clockwise direction. So that's basically the most important part of the problem. By using Faraday's law, just compute the EMF. Next, we are asked to find the forces that are applied. So let's just draw these again. Let's just remember that at this point the magnetic field is towards us. At this point the magnetic field is away from us. So there's a current flowing in there. The current is like that. So what's the value of the current in here? So that's along that direction. It is the EMF prime divided by the resistance. But I forgot all the values that I have computed. So the EMF prime was plus 3 volts. And the resistance was 6 ohms, all right? So that means 3 volts divided by 6 ohms. So half an ampere is flowing along that direction. So let me draw the current like that. So that means I'm going to show the forces with a green color. So on this side, what's the direction of the force, magnetic force? Force applied by the magnetic field on the side. So the force would be, let me call this as F1, or let me call it as F1. So that's going to be equal to the current multiplied with that length crossed with the magnetic field in there. So the length vector is pointing downward. Magnetic field is towards us. So by the right-hand rule, this F1 force would be leftward. Right, that's the direction. What's the magnitude? The current is 0.5 amperes. Length was, I think this was 2 meters. Yeah, it was 2 meters. And the magnetic field was 2 Tesla. So it is 2 Tesla. I don't want to write down any unit vectors in here, so that's just the magnitude. So that means it's 2 newtons towards left. Let's talk about the side now. Since the magnetic field also has changed direction, you can also see that the force on that side is going to be in the leftward direction. Why? The current is the same. The length vector is now is in the upward direction, and the magnetic field is downward. So by the right-hand rule, length is upward, the magnetic field is downward, so therefore the force is towards left. So again, I'm going to write down the magnitude. Current is 0.5 amperes, the side length is 2, magnetic field is now 3, so that means this is going to give us the 3 Newton value. So as a result, there should be an external force applied in here. We should be applied in the rightward direction. The external force should be essentially equal to the sum of these two magnitudes of these two forces. So that's F1 plus F2. So that would be 5 newtons. So I need to apply a force in the rightward direction, which should be equal to 5 newtons. Why didn't I count in the forces on these two sides? The reason is that they just cancel each other. I know that from experience. So the force on that side cancels with that force. and force on this side cancels with that force, so I didn't include these. But of course, in the actual calculations, of course, I need to compute the total force applied by the magnetic field on the frame. But since they cancel each other, I didn't bother computing these forces. So the 5 Newton force towards left is the total force applied by the magnetic field. To make sure that the net force is equal to 0, I have to apply an extra 5 Newton force in the rightward direction. Let's remember this from the point of view of the conservation of energy. We have said that somehow this is moving towards right, but because of this there is an induced EMF inside, and so therefore the current flows, and because of the current flow there's an ohmic loss of energy, so this energy is converted into heat. So there's something in here, a mechanism that consumes energy. Where does that energy come from? Well, it can only come from the kinetic energy of the frame. So as a result, this is going to slow down. So therefore, if I don't apply an external force, then the magnetic force acting on the frame should try to slow this thing down. I don't mean that it should always be exactly opposite to the velocity. This is not necessarily true in all cases. We have seen some examples of that. But at least it should have some component opposite to the velocity, so that it has the effect of decreasing the translational kinetic energy, right? And that's what we are observing in here. So the magnetic force is in here. The magnetic force, the sum of these two magnetic forces should be opposite to the velocity. So since they are in the same direction as the velocity, they should be opposite to that. So because their function is to decrease the speed. So it's like a friction basically. So as a result, to prevent the frame from slowing down, I then need to apply this additional force. So then let's talk about the power, the conservation of energy, right? So that's the power, let's say, given by external force. Let me just call this as power external. So that's the external force dotted with the velocity. Since we have said that these are just along the same direction, so this is therefore is equal to the product of the magnitude. So force was 5 newtons. Velocity was, I need to remember that value too. Velocity was 0.3 meters per second. So 0.3 meters per second. So therefore, this is 1.5 watts. And then the power consumed on the resistor. Resistor is on the frame. So that's the ohmic loss. So that's equal to I squared R, or if you want, it is E squared over R. I again forgot everything. I think current was 0.5. But let's remember the values. Resistance was 6 ohms. So I'm going to use this formula as 6 ohms, and the current was 0.5. So that's 1/2, 6 over 4. So that's also going to give me 1.5 watts. So as a result, the external force provides energy to the frame. It is 1.5 watts. And the frame uses that energy by converting into heat.